Okay, so hello everyone. Welcome to the week 6 of problem solving session for the design and analysis course. So, what will last time we saw this MST and union find data structure and how you can implement it um, efficiently by making a clever choice of data structure. So in the upcoming weeks, um, I guess there are only 3 more weeks for the exam. So the theme of this week is going to be one paradigm of algorithm, which you've already seen. It's called greedy algorithms. And the other paradigm that you have seen in previous algorithms, the shortest path algorithms and the minimum spanning tree algorithm, the other thing was dynamic programming. So this is another paradigm, and this week we'll only look into the greedy algorithms, and this is something we'll do in the week 7. And just to give you an idea about how we are going to conclude the course, so what we'll finally see is that so what we'll finally do is, so far in the course you have seen some problems and how do we design algorithms for them, what is a correct algorithm and so on, and how to do the time analysis and so on. Finally, what we'll see is that there are problems for which we don't know if there is an efficient solution. We don't know if there exists one. And we'll look into those kind of hard problems. And there is a neat classification that we have done. So, given a problem, where do you put it? Do you put it in the class of efficiently solvable algorithms, or do you know they are hard and you know how to prove them, or you don't know any of this? So, easy versus hardness of problems, and we will properly define what we mean by them. So this is called intractability, and this will be the final theme of the this is the final theme of the course. And finally, on Monday, which is 17th, I think exam is on 18th. So on Monday the 17th, we'll have a final summary or short summary session. If you have any questions, you can you can participate in the final session. Okay, so let's start with the theme of the greedy algorithms. So do you recall any greedy algorithms that you have seen earlier?
Dijkstra,
Dijkstra. Dijkstra is one. Good.
Kruskals,
Kruskal's.
Prims,
Prim. Yeah. Okay. Good. So so these are the uh, three greedy algorithms that you saw, and we did not formally prove the correctness of any of them. We never argued why it always gives you the correct answer. So that's something we didn't do. But if you are interested in knowing, then good resources, again, the 3 textbooks that I've been mentioning throughout the course. One is CLRS, then the other is Kleinberg Tardush, and the other is, if you want more problems to practice on, then um, then Das Gupta is a good reference. So Das Gupta, Papa Dimitriou, and Vazirani. So this is just one book, DPB you can call it. So you can look into the 3 for correctness and so on, and for more practice problems also. So we'll do for the data structure parts, there are 2 things that are relevant. So data structures that we'll look into is, one is what is called the binary search tree, the other is what is called an AVL tree. So before we get into the data structures, we'll quickly talk about the greedy theme. So greedy algorithms, and what we'll look into today is just the Huffman encoding. Okay, So let me start with that. um, okay. Okay, so the problem is very simple. So you have this huge files, mp3. It could be any file, it need not be just a text file, it could be an audio file, it could be a video file, or it could just be as simple as a text file. And let's say the file is very large, so it's something like maybe maybe it's like 256 GB or something, let's say. So it's very um, maybe like 25 GB, and it's very large. So if you want to send it from your computer to your friend's computer, then that amount of data has to be transferred from your machine to the other machine. So naturally, one thing is you are losing lot of resource would be computation, could be time, it could be your data itself, storage, and so on. So that's something you don't want to do. You don't want to send large files like just like that. So then what do? You do something that's called a compression, which is something you use in your day-to-day life, right? So what you need to do is you somehow need to compress this data, this large amount of data, into, or let's say, reasonably smaller file. So maybe if I can bring it down to few MBs or something, then I can then if I can some way send it to your friend's machine, it's the same file. And then if there is some uh, um, decrypting decryption algorithm which will take that compressed file and get back the original data, then your friend can now enjoy the same music. So now you can get back the uh, you can get back the whole file, send the file that way. So what we need to understand is how do we do this compression, okay, and how do we do the decryption efficiently. So these are the two things that come up. So um, one of the most natural things that you would do is, let's say, um, yeah so maybe I have some data, I'll just write random. Okay, so I've so okay, so let's say you have some part of data which looks like this, and of course there may be so many other characters. um, yeah, there could be a lot of characters, but right now I'm not writing, just for the sake of ease. And you want to send it as a binary encoding. So what you could do is, one way to do, so how many characters are there? There is B, C, D, E, um, F, and G. These are the five. These are the six letters that you have. So, if you can observe this, you know that um, every alphabet or every character has an ASCII value associated with it. That means you have, say, all these possible um, you have all these possible letters, and then there is an 8-bit string that is associated with it. So for example, 00, I want to write A like this, then B could be something like this. So there is a standard encoding which converts your alphabets in English into a binary string for the computer, and each of them is guaranteed to be 8-bit string. So what will happen is, you'll use the ASCII encoding for B, that is itself 8 bits, and then you'll use the ASCII encoding for C, which is again 8 bits, and so on. So then you will eventually get this as a binary string of zeros and ones. So what will be the length of this encoding? So if this is the message that I have, or this is the file that I have, so how many characters are there? They're 12, right? Okay, so by that we mean that so the length of this message would be the number of characters into it, which is 12 in this case. So for each of the 12 characters, you are using 8 bits. So totally how much is the length of the encoding? Is this okay? Is this okay with everyone? So huh. So basically what we just said is that for each of the letters you're going to replace it with a binary string of 8 bits, and therefore the total length of your encoding would be 8 times the length of the message, which is really bad for us. Why is that? Because yeah, which is really bad for us because um, if you notice in this particular message, there are some alphabets that are not even going to be used, and I'm still using so many bits to represent them. So this is the problem. So if I could instead create my own mapping where I map B to let's say 000, C is 001, D is 010, E is 011, F is let's say 100, and G is 101. Okay, if I create a mapping like this, and now if I do the encoding, then how much bits will it take? So for every alphabet here, I'm going to replace it with a string of length 3. So this becomes let's say 000, this becomes 001, 010, and so on. So what is the length going to be? Yeah, exactly. So it's going to be 12 into 3, which is 36. Okay, so just by using this fact that I'm not really using everything in the alphabet set, I'm just using a few of them, I can actually bring down the length of the encoding from 96 all the way down to 36. So this is the main idea behind compression. You're going to remove the redundant information and use only what is needed. So you can create your own mappings like this, so that the this compression happens as you can compress it as much as possible. So one such idea is by Huffman. So we'll see how to what it does. So far what we did is just a very naive um, way of doing. Okay, there is one comment in the chat. Alphabets are 6 and the string. Okay, yeah, that is correct. Okay, okay, okay. So let's just look at one simple example again. So let's say I have a string like this. Okay, and in this case I only have maybe I'll write a few more. Okay, now in this case I have uh, some 4 5 letters in my alphabets in my string A, B, C, D, and E. Okay, and now what you can do something like earlier. You can say that maybe A is 000, B is 001, and so on. You can do something like that. So it will take 3 bits per character. Okay, but notice that there are some alphabets that occur more often than other. So what I would want to do is for the ones that occur so many times, if I could somehow just use this, reserve this bit 0. So whenever I write 0, I just mean, let's say, A. Then what will happen is, how many times does A occur? So frequency of A is the number of times A occurs in the string. So which is in this case 6, right? There are 6 occurrences of A. So if I encode A as 000, then I'm totally spending 3 into 6, which is 18 bits for encoding A in the whole string. Okay, but now that I know that A occurs so frequently, if I could somehow, let's say, encode A as just 0, then I'm actually using only 1 bit per occurrence, so which is 1 into 6, which is 6 bits. So instead of 18, I'm bringing it down all the way to 6. Okay, so this is like the idea of Huffman encoding. It says that don't just blindly encode your alphabets with same number of bits each time, which is what we did earlier. We did 3 bits per alphabet, but rather you notice the frequency of, maybe like do one scan of the entire message and find out how frequently a particular alphabet occurs. So can you tell me the frequency of the other alphabets here? So what is the frequency of B? B is 3. Yes. C, C, D and D are all 1. Yeah. Good. Okay. So so what that means is, so for example, if I encode C, if I end up encoding C um, as maybe 111, okay, that is okay for me. I'm still paying a large price for C, but that's okay because I'm only paying it once here. It only, anyway, it occurs once, so I'm okay with spending few more bits there. Similarly for TNE, because it's just a one-time cost, it doesn't occur a lot of times. So with that in mind, how much if you do this encoding, so let's say I encode A as 0, B as 1 1, C is encoded as 1 0, and D is encoded as 1 1 0, and let's say A is encoded as um, okay, maybe I'll do this. Okay, just give me a minute. Okay, let's say I do this kind of encoding. So A is mapped to 0, B is mapped as 101, 100, C is mapped as 101, and so on. So if this is the encoding you follow, that is, you replace every occurrence of A with a 0, every occurrence of B with a 100, then what is the total length of this message if we follow this encoding map? So what is the total length? Okay, so Ayuti says 24. Let's check that. So there are 6 occurrences of A. For each of them, we are spending 1 bit, so that is 6. For B, um, we are using 3 bits, so that is 9. For C, we are using 3 bits, so that is 3, and for E again we are using 3 bits. So what is the sum of this? This is 18 plus 6, which is 24. So 24 is what you'll end up using. Whereas if we would have, if I mean, just contrast it with the previous method where each of them had a 3-bit string associated with them. So if we do that 3-bit encoding, then how much would the length have been? there's a raised hand. Krishna, do you have a question or okay? So there are 12. The length of this message is 12. For each of them, we are using, if we use 3 bits, then the total, yeah, the total length of this would be 36 bits. Okay, so this is just to contrast. So if you just blindly do a 3-bit encoding, you would have used 36, but if we do something clever, which is look at the frequency, then we are saving on the number of bits that we used. So this is the main idea of the Huffman encoding, and what it tells you is how to come up with the best map, with a map as best as possible. So this is something that we just tried out. I mean, we just tried some values and we came up with this, but is maybe there is a possibility that we can do something better. Maybe there's some better map than this, which will even bring this 24 down further. So that is what Huffman does. So what it says is, now we'll look at the idea of Huffman encoding. So what it says is, whenever you get a message, first thing that you do is you scan through it and write down the frequencies of each of the alphabet. And now we have these values 63111. Then what you do is you write them in the sorted order, in ascending order. So what is the sorted order for this? That would be 11136. This corresponds to maybe A, B, C, D, E, doesn't matter. So then what you do is, now that you have written them in the sorted order, you're going to pick the minimum two smallest values. So which are they? What are the two smallest values here? Yeah, so C and D. Yeah, you can take any of the two out of this. So C and D, let me take C and D, and then what I'll do is I'll combine them together and form a node. So this comes from the idea of trees that we saw earlier. So I'll just combine these two and I'll form a node, and I'll write a value at it. So what will be the value at this? It will be the value of the frequency of C plus the frequency of D, which is in this case 1 plus 1. So I'll write a 2. Okay, now what you do is you think of these and this new value as your set, and now you pick the smallest two again. So these are out of the question because we already dealt with them. The boxes are out of the question. Look at the remaining values and find the next two minimum. So which is that? Okay, this is also in the set. So you are looking at 2136. One and two, exactly. So now we will do the same thing, combine 1 and 2 and form a node. And what is the value that we will write? That we'll write the sum of the two values that we just combined, which is 3 in this case. 2 plus 1, 3. Now this is also done. So what? Okay, so now look at the next two minimum, which is amongst these three. So what are the next two minimum? 3 and 3. Good. So then we now combine 3 and 3 together and we get a tree like this. And finally we only have two elements remaining now, which is 6 and 6. So there is no choice, we are going to combine 6 and 6 together and we get a value of 12. Okay, so now what it says is you're going to write 0 on the left. So each node has exactly one left edge and exactly one right edge. So we'll write 0 1 for 6 also. On the left side you write a 0, on the right side you write a 1. So 0. So 0 1. Again do the same thing, left is 0, right is 1, left is 0, right is 1. Okay, now what we are saying is we have actually encoded all these letters by using this tree. So what is the encoding for A? We want to find the encoding for A. I'll start with the root, which is 12 in this case. Start from 12 and reach all the way up to A. So what did I read? I only read 1. So the encoding for A is just going to be 1. But let's say I want to encode B now. So how do I go from 12 to B? What is the path? I'll go like this. So what is the encoding? It is the value that you read on along the path, which is 0 followed by a 1. So encoding for B will be 0 1. Now similarly, what is the encoding for C? Exactly, it is going to be 4 zeros, because if I want to reach from 12 to C, then I'll take a 0 0 0 0, and then you want to go from let's say quickly, maybe encoding for D and encoding for E. Yeah, so it's 0 0 0 1 and 0 0 1. Okay, so okay, good. So you can now using these as your encoding. So instead of having this map, if I give you this map, you can try to find out what is the compression length of this message if I use this. Okay, but we'll do such examples. But the point that I want to convey is that um, the um, the Huffman algorithm basically what does is it writes the frequency in the ascending order, and each time it looks at the new the unassigned values that you have, finds the minimum 2 and creates a node and updates the value of the node until you have basically made all of them the leaves. So yeah, and then we use the property of the tree here to find out this encoding, because in a tree, if you look at any leaf, there's going to be exactly one path. There's a unique path from the root to the leaf. You can't have two paths from root to leaf. Do you see why? What will it contradict otherwise? Exactly, good. Otherwise, you end up getting a cycle. So, if you have two paths like that, then you will end up creating a cycle. That's why. So, this is the property that we are using to make sure that we have an encoding function. That is, you cannot have one character and have two possible encodings for it. So, this is the simple algorithms. Now, what we'll do is we will see some examples on based on these. Okay. Before that, are there any questions regarding the algorithm? Okay, good. So
Hello, ma'am.
yes.
Ma'am, I have a doubt in binary heaps, ma'am.
Okay, so can I take it up after we
Ah,
finish?
okay, ma'am. Okay,
Okay,
ma'am.
okay, sure. So yeah, so just take this example. So the symbols that you have are A, B, C, D, E, and these are the frequencies. So frequency of A is half, frequency of B is 1/4, and so on. And now we are going to use the Huffman encoding technique, and it will tell you how to encode A, B, C, and so on. So just apply the algorithm and let me know what are the encodings that you get. So I'll wait for a couple of minutes in case you are trying. Okay, so those who are trying, you can if you come up with answers, you can write in the chat. I'll take a look at it. So let me start solving. Okay, so the frequencies that are given to you are precisely these, and the first step that we know is first step would be that you sort them. So what is the order? Um, okay, so the order would be 1 over 16, 1 over 16, 1 over 8, 1 over 4, and 1 over 2. Okay, so this is the ascending order. Now what do? We take the first two minimum, which are these two, and combine them together as a node. And what is the value that we will write? What is the value of this node? So just recall what we did earlier. So we looked at the frequencies here and we simply added them. So what will we do? We'll just take the sum of these two. So what do we get? Okay, so we get 1 over 8. And now what are the next two minimum? Okay, is the algorithm clear to everyone? So okay, maybe if it's not, then maybe we'll run this example again. If there are any questions after that, then please let me know. So then we look at the next two minimum among this set, which is 1 by 8 and 1 by 8. So we combine them, and what is the value that you write? It will be the sum of 1 over 8 and 1 over 8, the nodes that we combine, which is 1 by 4. Then you look at the next two minimum, which is 1 4 and 1 over 4 here. Then again we combine them together. So what is the value that we get here? It's the sum of these two, which is 1 by 2. And finally, what are the two minimum nodes that are remaining? It's half and half. So we combine them together and we write this. Okay, so now we follow the same steps. We just write 0 1 0 1 0 1 0 1. It doesn't matter where you write 0 and where you write 1. It should just be that one of the branches is 0, the other branch is 1. It can be in any order, but they should both be distinct. Okay, good. So I think Ramnathan has correctly answered this. So you have A, B, C, D, E, and the encoding for A is going to be 1, encoding for B is going to be 0, 1. Then you have 0, 0, 1 for C, 0, 0, 0, 1 for D, and 0, 0, 0 all zeros for E. Okay, so um, okay, so good. So now can you try the part B? So what it says is you have a large file. It has 10,000 characters. There are 10,000 characters in it, out of which half of them are going to be A. That is sorry, this is 1 million, right? So yeah. So half of these are going to be A's, 1/4 of these are going to be B's, and so on. So if you have such a file, what is the total length of the encoded file when you apply this scheme? This scheme here. It's okay if you don't calculate. If you just tell me the expression, that would be enough.
Hello, ma'am.
Yes, yes.
I think we should multiply with 1 by 2 with 1 million plus for B we have 1 by 4 into 1 million plus 1 by 8 into 1 million plus 1 by 16 into 1 million plus 1 by 16 into 1 million.
Yes, that is, yeah, that is almost correct, except that one thing that we did not count here is the bits that we are using to encode each of them. So for B, for example, you're using 2 bits, so you should also multiply it by 2.
Yes, ma'am. Yes, ma'am.
Yeah, good. So for A, the length is just 1, so it doesn't matter. So for A, you're going to take 10 to the 6 into 1 by 2 into 1 bits. For B, you're going to take 10 to the 6 into 1 by 4, because 1/4 of them are B's. For each B, you are using 2 bits to encode. So this is what you'll get. For C, you have 10 to the 6 times 1/8 of them are C's. So these many C's you have. For each of them, you are using 3 bits to encode. So this is what you get. For D, you will get sorry, I think sorry, both are
For
both
E,
are
4,
4.
4.
Yeah, both are 4. Yeah, thanks. So this is 4, and if you add them together, you will get your final answer. So just sum up all these values, and that will be your final answer. So are there any questions? Are there any questions regarding? Um, okay, okay, good. So okay, so maybe in the interest of time, I'll not do this question, but try this out. It's similar to what we did. You just have to convert them into frequencies and then apply the same algorithm. So we'll not do this. Maybe I'll move on to the next question. So okay, just 2 of them. So maybe we'll do this one. So what the question says is you have 3 alphabets only. It's ABC, and their frequencies are FA, FB, and FC. Okay, and now we're going to apply the Huffman encoding on them. So if you, let's say, apply the algorithm, and the code that it gives you is 0, 10, and 11. That means one of these gets 0, the other gets 1, 0, and the other gets 1, 1. We don't know which one gets what, but the question is it possible that such an encoding can happen? If yes, then you have to come up with some values for FAFB and FC, such that if you apply the Huffman algorithm, you'll get this code. Otherwise, if it's not possible, then come up with a reasoning why it is not possible. So um, yeah, so just take some time, think about it, and then share your ideas. So for part A, do you think it is possible to get such an encoding, such a code? How many think it's possible? Can you, um, yeah, maybe use a reaction or use the chat? Okay, so let's see the answers. Sorry. Okay, so the answer for this is yes, it is indeed possible. So we'll um, just come up with some examples. So let's say FA is 2, FB is let's say 4, and FC is let's say 7. So then apply the Huffman algorithm on these frequencies. So what you have the sorted form 2 4 7. You choose the first two smallest values, which are 2 and 4, then you combine them and you get 6 here, and then you combine the next two remaining values and you get a 13 here. And now if you do the same labeling 0 1, or maybe I'll do 1 0 1 0, then okay, it doesn't matter which is A, which is B, which is C, I'll just do randomly. Then one of these gets encoding of 0, which is what we have here, the other gets a 1 0, which is what we have here, and the other gets a 1 1, which is what we have here. So I have given you some frequencies for which if you apply the algorithm you'll get these encodings. And yeah, like we remarked earlier, there is no strict rule on which side is 0, which side is 1. You can fix a convention for yourself, but yeah, you just have to ensure that the two branches should get opposite values. That's it. So is this clear? Is the part A clear? Okay, if yes, then can you try B and come up with frequencies, or come up with an argument if it's not possible? Yeah, frequencies can be anything. You come up with frequencies such that if you apply the algorithm you get this code. It could be anything. So did anyone come up with some frequencies? Feel free to share if you have any partial thoughts or any ideas. Okay. Okay, so does anyone think it is not possible? Maybe yes or no answer. Do you think it's possible or not possible? Exactly, yeah. B is not possible. So do you have any, I mean, just random guess or anything for why it cannot be possible?
I took A1,
Okay.
B2, and C3.
Okay. Yeah, so for these values you can't get, but sorry, so for these values you can't get, that is correct, but the question is it possible that I can come up with some other values such that for those values I get this encoding? So for this one I agree we don't. Okay, so the question is, if you want to say no, then you have to say that no matter what FA, FB, FC you write, it can't happen. And if you want to say yes, then you just have to come up with some FFP, which is what we did here. I just want to say yes, then here is one example. If I want to say no, that means for no values, I mean that's what we are saying here, no matter what frequencies you put, you can't come up with this encoding. Okay, so so how do we show something like that? So the idea is that um, if let's say such an encoding is possible in the Huffman, then what will the tree look like? The tree will look something like this. It has some root node. From there you have a 0, you have a 1, there is some leaf here, and you have some leaf here at 0, and then further you have a 0, and you have some leaf here. So I think you might have guessed by now that all the leaves that you have are only, I mean, all the characters you have are only at the leaf level. You cannot have a leaf somewhere in the middle like this. So these squares are somewhere that's already at the bottom. These are your characters, and these are just internal nodes that are never being used. So um, so intuitively what's happening is it's saying that this is also a leaf, this is also a character, and this is also a character, which if you apply the Huffman algorithm you'll never get, because what it does is it already starts with these three leaves at the bottom, and it's going to combine in some order. And there is a reason why this cannot happen, so this is just something you can conclude from the algorithm, but the reason why it cannot happen is because of sanity checks. So for example, um, if I give you a code, maybe let me take the first example, and I'll give you a random uh, binary string. Okay, I'm just writing some random values. mm, okay, if I give you this string, this binary string, and let's say that a is 0, b is 1 0, and c is 1 1, and from this string you want to extract the abc data. Okay, so this is the decryption part which we mentioned earlier. So this is the compression part where we use the Huffman encoding. Now your friend has this file and they want back the file that you sent, so they're going to do some kind of decompression. Okay, so how do we do that? What we'll do is you look at the first bit and you know that 0 is definitely an a, so you write an a here. Next you look at 1, there is no um, there's no I mean string, there's no character here which has just 1. Then you read the next 2 which is 1 0, so then you write a b. Then you read the next one, there's nothing for 1, so you read the next 2 which is 1 1, you replace it with c. Can you complete this quickly? Like, can you just tell me what is the data here? Okay, so for 0 you have a, for 1 0 you have b, for 0 you have a, 1 1 you have c, for 0 you have a. Okay, this one is not even possible, sorry. So sorry, this shouldn't even be there. So notice that there is, yeah, good. So notice that there is one nice thing about this string, which is that no matter how you read it, there is only one possible interpretation from it. You cannot get two possible interpretations from this code. And but if you look at this example, and if I give you something like this, maybe, then if you read the first 0, then you can interpret it as a. But if you read read it as a block of two zeros, yeah, exactly, yeah. So if you read it as a block of two codes, then it could even be, maybe there's no a here, but it's just a c. So that's also possible. So you cannot, ideally your a good code should not have two interpretations. And like Ramanathan has correctly pointed out, you if you generalize the property, you don't want one code to be a prefix of the other code. That is exactly the property that we want. So maybe I'll just write it. So the property that we want is node code should be a prefix of the other. Okay, So we don't want that, otherwise there is no unique interpretation that is possible. So okay. Hmm. So this is what is happening in this example, and Huffman coding makes sure that it is in fact a coding which has this property. This is something you can see from the algorithm itself, and because this does not have the property, this is not a Huffman code, so you can never get this. So is this clear? Okay, so okay, there is a question. What if we had one at the end of that string which is not present? Do you mean this string or this string? This string, right? The second one, first one. Okay, then it's not a valid. Encoding itself. So not every binary string is a valid encoding. Only some of them will be valid. Is it okay? Okay, good. So what about third one? If you observe, it does not have the property that we just now observed, right? There is no string here which is a prefix of the other. So then is this a Huffman code? No. Good. So why is that? Okay. Um, None string are getting mapped with respect to property. You mean this property of prefix free? Okay, so this property is satisfied because there is no. If you look at any two encodings here, none of them is a prefix of the other. So when I say prefix, the whole thing should appear before. I mean, this entire code word should be there before some other code word. So the entire thing is a prefix of the other. Only then you say it's a prefix. Okay, in other words, if it's prefix free, which it is in this case, if you look at any random binary string, let's say this, there will be a unique encoding for it, because what you will do is all three of them are blocks of two. So you basically break it into blocks of two, check if it is 1001 or 00, and then map it accordingly. So there is a unique decoding for this that is possible, but the problem with this is that, so answer for C is no, it is not a Huffman encoding. So why is that? Because you have three characters, right? A, B, C, in some order, doesn't matter, and they have some frequencies, and these are in the ascending order. So let's say like this. Then what it will do is, I don't know what the values are. It will take the two minimum. So let's say these are the two. These are the two minimum. It will combine them like this, and then there is no other choice. It just has to take this and combine them together. This is the only way it will work. Okay, by the definition of, by the algorithm. So then you do some any kind of assignment, you will see that there is always one alphabet which only gets a encoding of length 1. Okay, this will always happen because of the way the algorithm runs. And then there will be two which have 2-bit encoding, and what this does is, it actually gives a 2-bit encoding to all of them, which you cannot get if you run the Huffman encoding, and which is good for us because this is taking more bits to store, right? Something that I could just do using 1 bit, I'm actually spending more bits for that. So Huffman kind of ensures that you spend as minimum as possible. So there's a proof for why Huffman would give you like a compressed, a good encoding. There's a proof of correctness for this, but we'll not get into the correctness proof for now. But it is, if you want, if you can look it up in one of the books that I mentioned. Okay. And okay, so are there any questions regarding what we did right now? Okay, good. So okay, so maybe this is a quick question. So we'll end up the discussion of Huffman with that, and yeah, we'll move on to the data structure part. Before that, just quickly try to answer this. So you have n symbols and alphabets, and these are the frequencies f1 to fn. The question is, um, what is the longest code word that you can possibly have? So there could be lots of different trees possible based on the values of f1 to f2. What is the longest such path you can find? And if you can find, can you come up with an explicit values of FIs, um, which would satisfy the claim? Okay, good. Yeah, so I think if you meant n minus 1, yes, then the answer is correct. So what could happen in the worst cases? You have these frequencies arranged in the ascending order. You take the minimum and you combine them together. Okay, then it's possible that this one and this one are still the next minimum. Then you combine them together. Then maybe this one and the next one are the next minimum, and you keep on doing this. Finally, you will end up combining the previous one and this. So, what is the um, longest path in this? The longest path is this that reaches to f1. So, what is the maximum height of this? It can be n minus 1 if you count it. So this is 1, then you have 2, then you have 3, and so on. So for f1 you have n minus 1. So the longest path you can have would be n minus 1. And if you want, you can come up with a simple example, which is you write a 1 2 4 8. Basically write the powers of 2, and you will always see that if you add 1 plus 2 you get a 3. So the next smallest is 3 and 4. If you add them you get a 7. So the next smallest is again 7 and 8. So you combine them, and it keeps on happening like that. And the longest path here would be of n minus 1. So this is an explicit example of when we can produce these frequencies. So if you want to see why this is maximum and why can there not be any other tree which has you can think about it and try to prove the correctness of why this is the maximum you can get. Yeah, but if there are any questions about the Huffman encoding in general, then this is a good time to ask. Then we'll switch to the data structure part. Okay, so if you want more examples to practice, you can take a look at the Tardosh book, and there's a chapter called Greedy Algorithms, and you can find some nice solved as well as unsolved examples in it. So before we move to the data structure part, I think there was a question about heaps. Um, I can address that now. So what was the question? I think Ramanath.
Ma'am,
Yes.
ma'am, what is the time required to update a value in heap, ma'am?
Okay. So you are saying you already have a heap. and you want to update some node in it.
Yes, ma'am.
Okay, so the standard operations that you have is insert and delete, right? So you can think of update as two operations. One is that you delete the node that you want to update, and then you insert the new value that you want. So the time for update would be the sum of the two, which is log n.
Okay, ma'am. I thought first we need to locate that element, then we need to change the value. So I thought it's n log n, ma'am.
Oh,
So
okay,
in
okay.
previous lecture, you have discussed about decrease key procedure, ma'am. So
Ah,
in
okay.
that I have a doubt.
Oh, okay, okay.
Thank you.
Okay, sure. Okay, good. So yeah, so let's move to the data structure part. Okay, so I'll just quickly start by defining um, what is a binary search tree. It's called also called a BST, and it's basically a binary tree where each node has satisfies a certain property. So let's say I look at this particular node, and the what are the two children? This is the left child of this root, and this is the right child. Similarly, if I think of this as my, if I forget about the whole tree, and if I just look at maybe this subtree and I forget about the rest of the part, if I think of this as my node, and this is the left child, this is the right child. And what a binary search tree basically says is that if I look at the value at the node, the value of its left child can be at most the value of the right child, and so on. So for example, if I write um, yeah, if I write 10 here, then 7 and I write a 7 here and a 13 here, then it satisfies the property. Similarly, if I write a 3 here, 6 here, it satisfies the property that the value at node is larger than or at most the value of the immediate left child and that of the right child. And this property recursively holds for every node. So if I look at this node, the value here should be at most 13, the value here should be at least 13. Same thing happens, sorry, this is not 6, I can have 8 here. Okay, but can I have maybe something like, sorry, can I have something like 13 here, because 13 is larger than 7? Is that okay?
No, ma'am.
No, why is that?
Because 13 is greater than 10, ma'am.
Exactly, so the property is satisfied for 7 but the property is violated for 10. So yeah, so it cannot be yeah, everything to the left of this should be smaller than 10 and everything to the right of this should be larger than 10. So this is not correct. Okay, so if that is clear, just quickly just take a look at the 4 examples and tell which of them are BST and which are not.
A is not a BST, ma'am.
Okay, why is that? Which is the
12 cannot
culprit?
be the 12
12.
cannot be as
Yeah.
a left
12
subtree.
cannot be, yeah, so this is the problem. 12 is larger than 10. What about B?
It is also not a BST, ma'am.
Okay,
9
why?
cannot be at the right side of 10, ma'am.
9 cannot be, so this node is the problem, is at this node, here the problem is at this node. What about C?
It is a BST, ma'am.
It is a BST, but
That
why?
or machine.
D cannot be a BST, ma'am.
Okay, why?
7 cannot be a left child, ma'am.
Yeah,
To a
so
1 root 1.
exactly, so this is again the culprit node. Okay, so this is the only BST that you have. Okay, so I'll just quickly recall what in order, pre order, and post order traversal is. So, this is not something specific to a BST, it's something that's there for any tree. So, what does it say? Maybe I'll just quickly define what is in order traversal. So, okay, maybe let's do pre-order. This is something that you have seen when we did DFS and BFS algorithms, but I'll just quickly recall um, in order traversal. So what it does is it says visit, then go to the left, then go to the right. What does that mean? I start my exploration from the root node, which is 10, and I'm going to visit that node. That means I'll print the value 10. Then then what I'll do is I'll go to the, then it says go to the left, then you go to the left and repeat the same algorithm. Now think of this as your tree and repeat the same algorithm. So then what does it say? It says visit, go to the left, go to the right. So visit would mean that we print 7. Now we've done a visit for this. Now we need to go to the left. Left of this is 6. So for 6 again you use the same rule. We visit left, right. So visit would mean that I print 6. Left would mean I go to the left, so there's nothing, I come back. Then I go to the right, there's nothing, I come back. Now at this point for this node we have completed our visit, we have completed our left. Now we go to the right and apply the same process for this subtree. So what do you get now?
Ma'am, hello, ma'am.
Yes, yes, yes.
Ma'am, I think that the tree is not a BST, ma'am.
This is not a BST. So we are saying that this
Okay, ma'am, okay, ma'am,
holds,
okay, ma'am.
this holds for any tree. Okay, so what do we write next? We continue the exploration. So we were here, we did our visit, we did our left, now we are doing right. So on the right we have this subtree, so we do a VLR on this. Okay, so we are at this part and we are going to do VLR. So V means visit, visit would mean that print 12. Now you're done with V part. Now we're going to do left. So we go to the left of 12, which is 20. Now think of 20 as your tree and do a VLR for 20. So VLR for 20 means visit it first. So we visit it. Then you go to the left. There's nothing to the left of 20, so you come back. Then you go to the right of 20. There's nothing to the right. You go back. Now we are done with the VLR for 20. So we come back. So when we come back, we are at 12. At 12, we already did our visit. We already did our left. Now we are going to go to the right. So go to the right, but there is nothing. So you come back. You come back at 12. Now we are done with our VLR for 12. So you go back. You go back to 7. At 7 also we have done visit, left, right. All of that is done. So go back to 10. At 10 we have VLR. We'd already visited. We did the left part, which was this. This is already explored. So you go to the right. So now what do we do now?
We will first visit 14,
Visit
then
14,
13,
go to the
then
left,
13.
then visited 13. Then there's nothing here, nothing here, go back, nothing here, go back, and you're done with the VLR for this. So go back. So everything is done. Okay, so similarly you can think of in order traversal, where you go to the left first. After you have completed the exploration at left, you visit it. Once you have visited it, then go to the right and explore the whole tree. And there's something called post order, where you do LRP. Okay, so okay, so what we did here is, this is exactly the pre-order. Now you have to identify which of these, which one is the in order and which is the post order among the options that are given.
I think C is in order, ma'am.
Okay, C is in order, but that would mean if you try to do in order, so I'll just try to get no, I'll just draw the whole thing again, maybe 10 7. Okay, so if you do in order, that means you are doing left visit right, so you're doing left visit right, so that means you are at this node, you're going to go to the left, then you are at this tree, then you do left visit right, what it says is go to the left, so you go to the left, and then you get 6, you get LVR for this, and uh, at 6 you go to the left but there is nothing, so you come back, then you visit it, at this point only you visit it, print 6, then you go to the right, there's nothing, come back, so right is done, now go back, at 7 what you've done is you've completed the exploration for the left part, then you print 7, then you visit 7, then 7 comes, and then you visit the right part of it. So if you start with 10, that can only happen if you visit it in the first step only. So is this okay?
I said C is the in order.
Huh, exactly, so if you complete, yeah, good, so C is the in order, and yeah, and yeah, I think none of the answers that are there in the options corresponds to a post order traversal, so you can try to come up with it. It's an interesting exercise to understand how recursion works also, so try this out and come up with a sequence for the post order traversal, and then you can also ask, okay, why not define something like, you have this right, you always said that first you go do left, then you do right, every time left comes before right, you can even do the other way around, you can also define something like VRL, you can even do RVL, you can even do RLV, so this is also valid. There are different names for this, I think these are called reverse in order and reverse post order and so on, but will not these are not generally I mean, these are the ones that are very well studied, and so we'll just stick to this. So just try this out as an exercise. So now the interesting question that I want to ask is, what will happen if I give you a BST? If I give you a BST, is there anything special about one of these three traversals? So okay, my claim is that.
The
Hmm,
in
yes,
order traversal will be in ascending order, ma'am.
exactly. If you do an in order traversal, you'll get the sorted values. So the property of BST is that in order traversal gives sorted values, and the reason for that um, is very intuitive. It comes from the definition of a BST, which is when you do you have this node, you have a left tree, you have a right tree. When you do LVR, what that means is, before I visit the route here, I would have traveled all the nodes before it. So there will be some nodes that are red, then I visit this route, and then I visit all the other nodes in some order. So everything to the left of this is always going to be smaller, and everything to the right of this can only be larger, because of the property of the BST, which says that if you have a node, everything to the left should be smaller or at most that value, everything to the right should be at least that value. So this property recursively holds for every node. So similarly, when you come here, same thing will happen within this set. Before you visit this node, everything you visit before it will be smaller than it. everything you visit after it will be larger than it. Same property like recursively holds, and therefore this entire array will be sorted. So this is an interesting exercise. You can try to convince yourself if it's not clear. Okay, so the other question is, when I gave you a BST, there is a unique um, in order traversal, there is a unique pre-order traversal. There cannot be two in order traversals or any of these traversals. That there's one unique um, sequence that you get. The question is the other way around true? If I, let's say, just give you this in order, sorry, this was the in order traversal, then can you come up with this tree? Can you construct this tree back?
No, ma'am.
No. So there are multiple possible ways in which you can interpret it, right? So same thing happens for the rest of the traversals, but there are two of these that you can choose. Of course, if I give you three, you can always, so you can try this out. If I give you all the three, there is a unique tree that you can come up with, but I'm saying even two are sufficient. So which two are sufficient? Any guess? Like some some I mean, two of these are sufficient to construct the tree uniquely.
I think we can use both pre-order or post-order, ma'am.
Okay, so
For BST.
okay, okay, so the answer is you can use in order plus pre-order. If you use these two, you will uniquely get a tree. You can even do in order plus post order. This will give you unique tree. But if you do pre and post, this is the only case where you don't get, and there is a reason why. So I'll just try to hint you towards it, but I'll not prove it right now. But I think if you take some examples, you'll see what is happening. So let me just think of these two. I have pre-order and in order with me, and pre-order means I'm first going to visit, and then I'm going to the left, and then I'm going to the right. That means I know my route from this step only. So that means 10 is going to be the route. That is something I know from the pre-order. But now I can't tell which of these are to the left and which of these are to the right. So then I take help from the in order traversal. So 10 is somewhere here, right? So we are going to locate our 10 here, and in order you do LVR. So this part is the left and this part is the right. So that is how I know what is to the left and what is to the right. So then you go back to the pre-order sequence and see that 7 is the node that is visited next. So if you follow that sequence in pre-order, once you visit it, you go to the left. When you go to the left, you are going to visit it. So then you know that the next node is 7. So basically you do one step, use one information from pre-order, use it back to get into in order, and just keep moving back and forth between the two, and you will be able to construct the whole sequence using either these two or the other two. But the problem that happens with pre-order and post-order is that um, okay, you can actually come up with so there is no, it does not have this nice property. This in order sort of tells you what is to the left, the whole array that is to the left, and the whole values that are to the right, and that makes your job easier. But if you have pre and post only, you can't have such a nice distinction, what should be on the left and what should be on the right. So that can lead to ambiguity. You can even come up with examples where you have pre-order and post-order for it, but there are two different trees that you can construct out of it. So just take it as maybe a homework, and so come up with.
Ma'am, what I mean is, if they give pre-order alone means we can construct in order from the pre-order, ma'am. Then we can draw the tree, ma'am. We can sort it in ascending order means it will
Huh,
give the in
so
order traversal.
so yeah, So my question is, yeah, that if it's a BST, then it's correct. But if I don't necessarily give you a BST, so it's just for any general tree. Let's say for any tree I want to do,
then it is not possible, ma'am.
then it's not possible, right? So, yeah. So that's the only thing I've, yeah, good. Okay. So, yeah. Hmm. So now we'll just look at, we know what a BST is. Then some standard operations on that would be, um, you want to insert some elements into BST, you want to delete some elements out of it, you want to search for some element, and so on. So standard operations that you've seen on arrays. And yeah, so we'll just see how these operations are done. Okay. So okay, so let's start with the first operation, which says insert 13. So when I say insert 13, I'll create a node like this, and that's the operation. Then you do the next operation, which is insert it. So where should we insert it?
Left,
To the left of 13. So 8 comes to the left of 13. Then we want to insert 20
right of 13,
to the right of 13, because 20 is larger than 13. Then I want to insert 6
left of 8,
to the left of 8, because you start at the root. So 6 is smaller, so you go to the left, you go to 8, and 6 is even smaller than 8, so you insert here. Then I want to insert 10
to the right of 8,
to the right of it. So again, same thing, you start at 13, it's smaller, so it should be on the left. Compare with 8, it's larger than 8, so it should be on the right. So 10 comes here, and I want to do 42
right of 20,
to the right of 20. So larger than 13 and larger than 20, so to the right of 20 we have 42, and I want to do 16
left of 20, ma'am.
to the left of 20. So again, larger than 13, so go to the right, but smaller than 20, so go to the left. So 16 is done. Now I want to insert 30
To the left of 42, ma'am.
to the left of 42, and 45
To the right of 42,
to the right of 42. Good. So now comes the interesting part. All this time we were just inserting the elements by deciding whether to go to the left or right based on the value of the parent. So now I want to perform deletion. So before even going there, if I want to delete 6, then what I'll do is, I'll start at 13. The value I want to delete is smaller than 13, so I go to the left. Then I check with 8, again it's smaller than 8, so I go here, and now I found the node that I want to delete. So I'll just safely delete this node. I'll just remove this node out of the picture, and the resultant tree is still a BST. It's still a binary tree. This is okay. But let's say I want to delete 20. So where is 20? You will do the comparisons and find the node, and I want to delete it. So the problem is that we can't just remove the node, because then it will have these two hanging components which are not which do not form a tree. So um yeah, so then how do we delete? What is the natural way? So maybe I'll just remove these edges because 20 is deleted. So what do we do?
We can replace 20 with the maximum value in the left subtree or minimum value in the right subtree.
Exactly. So you have now two components, and you know that the value of, maybe I'll look at the right component. The value of these are all going to be larger than 13. That is something we know for sure because of the property of. So then this can be a right child. 42 can be a right child of 13. There is no, I mean, you just add it to the parent, to the right child of the parent, and that would be fine. But then now we have the 16. So what is the correct place of 16 in this tree? Where should 16 be?
Can be a parent of 42.
Huh. But I've already fixed this, okay? I mean, um, I've already made 13 a parent of 42, so I don't want to change that. Um, and the reason I don't want to do that is that there can be lot of things out hanging here. So this is a, in this case it's not, but sorry. Huh. In this case it's not, but it can have its own left subtree and right subtree. So if I add 16 here, again we run into the same problem. It already has its children, and then we now make it a parent of 42. So there are more pointers. That's why I don't want to add it here. I want to add it somewhere else. Then what is the correct position?
Left of 30.
Left of 30. Exactly. So now I add one more edge like this. And now this is your final BST. So if I draw it neatly, it's just going to be 16, and whatever is to the left and whatever is to the right. So generally the algorithm for delete would be that whenever you delete a node that has children, look at its parent and make the right child, attach the right child directly to the parent, to the right of the parent, and take the whole left side, and from this node you keep going, keep going left all the way, and then attach this. And why is left the correct position? Because of the property of BST, that this all these values are going to be smaller than, I mean, these values are always going to be smaller than any value here. So therefore it should be on the smallest, I mean, um, the leftmost child of this 42. So that's the general algorithm. It just follows from, um, from the properties. The question is, how much time does this take? So maybe just look at insert. How much time does it take?
Insert operation.
Hmm.
In worst case, it can take up to linear time.
Exactly. In the worst case, it can go all the way linear. So if you have like a very nice BST which is balanced, where if you have a balanced BST where, um, something like this maybe. Okay. So okay, then the height of this tree is going to be logarithmic in terms of the number of nodes. This is an exercise that we have done many times. So height of this tree is log n, and so in this case if you do an insert operation, then you are only traversing along a path. So you will, in the best case you go into log n, but the worst case that could happen is we never guaranteed that this would be balanced if we perform insertion like this. In the worst case it could so happen that, yeah, in the worst case it could so happen that the elements that came to you for insert came in this order. So it came 1 2 4 6 13 15 20. Then what happens is you inserted 1, 2 goes to the right, 4 goes to the right, 6 goes to the right, 13 15 and so on. So the height of this tree is basically the number of nodes that you have. So in the worst case the height can be order n, and therefore if you try to insert something you will always have to travel the whole length and then insert. So worst case insertion complexity is order n. And same thing happens for delete. I think you can see by now, that for delete also we have the same problem. So although BST um, has a nice structure that if it's balanced can help us do all these operations in logarithmic time, um, the problem is that it's not balanced, so the height can become very skewed. So what we want to do is we want to ensure that it's balanced. So yeah, so that is where this AVL tree comes into picture. I'll discuss about it. Before that, there are just a few questions you can practice on BSTs. We don't have time to get into it right now, but yeah, I'll just upload this whole PDF on the drive and do take time to solve this. So one question is you want to find the kth smallest element. So one thing is, where does the smallest element lie in the BST?
Hello,
Yes.
ma'am. I have a small doubt, ma'am. I am pursuing my BTech second year, so can I apply for an internship in the summer? Like in the summer, I will complete my BTech second year. Can I apply for that?
Um, okay, so directly
Means
there
I,
is.
means I have already got a top 1% in the IoT course last semester of
Mm-hmm.
NPTEL.
Okay, so directly I think for second years, we at least IITM doesn't have um, programs for directly um, I mean direct applications. But I think if you are keen on doing and if you have strong interest in research, I think you can personally mail the professors, maybe send them your CV and stuff. But directly there is no program for second years, but for third years there is a summer internship um, program. And sorry, and the criteria, I'm not sure if NPTEL toppers or if there's a criteria like that, but generally it will CGPA criteria would be there and from your institute. And yeah, I mean a strong motivation and a strong CV would be preferable. So
Okay, ma'am.
okay, good. So okay, so getting back to the question, so I'll just pass through it. Will not do it right now because I want to discuss the AVL. Um, yeah. So just okay. So if you get time, do attempt those questions. Some of them maybe we already discussed. Okay. So these are also called height balanced BSTs. Okay. And okay. So okay. So what we are going to do is the idea is very intuitive. The problem that was happening when we did, let's maybe take the same example. We inserted 2, we inserted 4. Okay. So the problem that was happening was that this chain kept growing like that. Okay. So for that, what we'll define is we'll define a notion of balancedness. When do I say a tree is balanced and when is it not balanced? So for example, if I have this node and there is a left subtree and a right subtree, if the height of this is 3 and 3 both are the same, then it's a balanced tree for me because um, yeah, because both of them have exactly the same height. If it's something like 3 and 4, then sometimes it's unavoidable because maybe it can happen that my tree is full like this, and now there comes a node for insertion, so I'll have to insert it like this. That can make its height 4 and this height 3 and so on. This kind of imbalance can happen. So one is the error of one, or the difference of one in the heights of the two children, the two subtrees, is something that we will tolerate. So if it's 3 3 4 3 or 3 4, we will say it is still balanced. So when do I say a node is balanced? Is that the height of left subtree minus the height of right subtree is at most 1, is at most 1. And yeah, so if maybe this becomes 5 at some point, then the tree is not balanced for us. So we'll say the tree is balanced if this property holds at every node, not just at the root. Then you look at the subtree, recursively the property holds for this node and within each of the subtrees, then you say it is balanced. Otherwise, if the property is violated for some node, then the tree is not balanced for us. That means we need to do something to make it balanced. So say that a tree is balanced if this balanced condition holds for every node. So yeah, that observation is correct. That means if I don't look at the absolute values, I just look at the difference, it can be -1, 0 or 1. Okay, so then what I need to do is I need to so maybe let's take the same example, and I inserted 1, I inserted 2. So what is the balanced factor at this point? What is the height of left subtree? That is 0. And what is the height of the right subtree? That is 1. It has a depth of 1. So if you look at the difference, here you have 0, here you have 1, the difference is mine. This node maybe let's say does not exist right now. Okay, so the difference is just -1, so this is still balanced. But now the problem is when I add this node 4, then what is the height of the left subtree and what is the height of the right subtree?
0 and 2.
0 and 2, and the difference is more than 1, so this is not balanced. So then what I'll do is I'll perform what is called a rotation. Okay, so yeah, so what we'll do is we'll rotate along this point and we'll make 2, or maybe that's not the visual way of saying it, but what I'll do is I'll bring this down and I'll bring this up. So 2 becomes the root, 1 becomes the left child, 4 becomes the right child, and it still satisfies the BST property when we rotate it this way. So now if we look at the height of the left subtree and the right subtree, it is now balanced, and we are still maintaining the BST property. So throughout the insertions that we do, there are several kinds of reasons why a tree suddenly becomes imbalanced. So yeah, so what we need to do is we need to each of the time we need to do some adjustments, some rotations, so that the tree finally becomes balanced according to the definition that we have. So yeah, so maybe let's take a look at what all kind of um, what sorts of imbalances can happen. So one is something that we just now saw, which is 1 to 4. So the imbalance was to the right and right. So in this case, the kind of rotation that we performed is called an RR rotation, what we did just now. It can also happen that you have 4, 2, 1. This is also a BST, and it also has violated the property of the height balanced condition. But in this case, the fault is on the left and left. So in this case, we perform what is called the LL rotation, and idea is similar. You bring this down, rotate it on this side and rotate it upward, so you get 2, 1 and 4. But just forget about. Okay, so this is what you get, and this is still a BST. And in fact you might have noticed that this and this is kind of a symmetric case. LL and RR are kind of mirror images of each other, so these are very similar cases. The other kind of imbalance can happen when you have 1, then you inserted 4, and then you inserted 2. So in this case, the again the height difference is evident, and what happened is you have 1 on the right and then on the left. So this is what is called RL. This is an RL type of imbalance, so you perform what is called an RL type of rotation. So any idea what kind of rotation can we do in this case to make it
First, we can make 2 as the right child of 1 mem, then 4 should be right child of 2 mem, then we can perform RR rotation.
RL, yeah. So yeah, so what you can do is you can bring this here, so that means 2 4, and then you can do this, so 1 comes here. You can do in any order. I think there are 2 orders that are possible, one, but yeah. So this is what you do, and the very symmetric case would be when you have 4 here, 1 here, and 2 here. So same thing happens. This is left of right, so LR rotation. You can do something similar and make it balanced. So these are the 4 types of imbalances that can happen. But now the complexity comes up when these also have children. So for example, this has children, this has a subtree, this has a subtree, this also has a subtree, let's say. Then what do we do? So maybe I'll call this T1, T2, T3, and T4. So so this is something we did, right? We did these kinds of rotations and we got this. Okay, but then what happens to these? So any idea where should T1, maybe let's see, where should T4 be in this case? Where should T4 be? Oh, sorry, T2 be?
To the right of T4 mem.
To the right of 4. Yeah. So
At first rotation.
hmm, yeah. So T4 is to the right of 4 because um, we're still maintaining the BST property. So everything here, sorry, I meant T2. Sorry. Um, yeah, sorry if I say T4 at some point. Okay, yeah. So we are looking at this subtree, and we know that all these values are larger than 4. So if there's something that is larger than 4, it will come to the right. So this tree remains intact on this side. Similarly, let's think about T1. So T1 has all the values that are smaller than 1, so it should come to the left of 1. So this remains intact, so this is retained just like it was. So this part, nothing has changed, and this part also nothing has changed. But it is 2 whose left child was removed, and we attached T1 to the left child, and its right child was removed, and we attached 4 to the right child, 4 as its right child. So now there are these 2 trees that are hanging, and we have not attached them anywhere. So the question is, what is the correct position for T3? So look at the values in T3. Those are larger than those are larger than 1 because they are on the right of 1, and they are smaller than 2 because they are on the left of 2. So that means we should go to the left of 2 and to the right of 1, because it's smaller than 2 but larger than 1. So this is the correct place for T3. So similarly, where should T4 go?
Left of 4.
Left of 4, because T4 is larger than, sorry, it's smaller than 4. It's on the left of 4, but it's larger than 2. So it's larger than 2, so go to the right, but smaller than 4, so go to the left. So this is T4. And similarly, the um, yeah, same questions arise when maybe we did RR rotation, LL rotation. It can maybe let's do this example. This is T1, T2, T3, and T4. So when I did the rotation, where should the T1, T2, T3, T4 go? So let's say T1. Where should T1 be? Maybe I'll just draw it again. Hmm. So what we did was we did 2 1 4. So where is t1? T1 is smaller than 1, so it's to the left of 1, so it should be to the left of 1. So t1 is intact. Then we look at t2. So t2 is larger than 1 but it's smaller than 2. So it's smaller than 2, so it should come to the left, but it's larger than 1, so it should come to the right of 1. So this is t2. Then similarly look at t3. T3 is larger than 2 but smaller than 4. So larger than 2 but smaller than 4, so the left child of 4, that would be t3. And finally similarly t4, it's larger than 4, so it should come to the right of 4. So yeah, so this is how we take care of um, all the subtrees that could be rooted at it. And I hope it's clear how performing the rotation makes the tree balanced at every step. So whenever we perform an insertion, if it so happens that the tree suddenly becomes imbalanced, then we are going to perform this rotation at every step. So that is the whole idea of the AVL tree. And yeah, and the question that we now want to ask is if it's okay. So the good thing about this is that it's height balanced. That's why if I want to, that's why the tree is always going to be logarithmic in order of log n, where n is the total number of nodes in the tree. So the nice thing about this is if I want to perform any kind of operations, say be it search or delete or insert, I can always do it in log n time. Okay, so okay, so so the question is, how do I detect that? Sorry, how do I detect that there is an imbalance? So maybe my tree is very large. I've already performed some 100 insert, delete, and so on operations, and I have a very large tree. Now I'm adding one node somewhere based on the BST property and so on. So how do I detect that there is an imbalance suddenly? I need to maintain some extra memory to know that there is an imbalance. So so what are the options? What can we do? Any ideas? What kind of information can we maintain at every node to check whether this balanced condition that we described earlier, this balanced condition is satisfied at every node, even after performing all this insert delete operations?
I think the key value we can say with height.
Sorry, can you repeat? The voice was not coming through. I mean, there was some break.
Hello, ma'am.
Yes, yes,
Hello.
yes, I can hear you
I
now.
think
Yeah.
we can save the height along with its key value as an element in node.
Yeah, so you can store the height along with the key value. That is something you can do, but um yeah, but um think just one issue with that could be that now you have stored the height, and okay, maybe that's not such a bad idea to do. You can do that. So whenever you update something, if it changes the height of that tree, then you are going to trace along the path. If it increases the height, you will increase the height of its parent and keep on doing that. So you'll have to keep on maintaining it. And every time if you want to check whether there is an imbalance, you look at the height on the left tree, look at the height on the right tree, subtract and check if there is an imbalance. Okay, but yeah, but the but the one problem that happens here with storing the heights explicitly is if I want to check if there is a if there is an imbalance, I'll always have to keep on subtracting. Whenever there is a change, I'll always have to keep on checking the node, look at its two children, keep subtracting and check whether, I mean, there is some way in which you can do this, but if I want to detect it very quickly, one thing you can do is just use this idea of this -101 that we yeah, maybe this idea of -1 0 1. So -1 if the height of the left tree is just smaller than that of right by 1, and so on. So you're not storing the whole height per se, you're just storing the balance factor of -1 0 1. So for example, yeah, so for example, in this case, if I look at this particular example, or maybe I look at this particular example, I look at this node, and the height of the left subtree is 1, the height of the right subtree is 1, the difference is 0, so I write a 0 here. This case, same thing happens, I write a 0, but let's say there was one more node of 3 here. Then what is the balance factor of 4?
My 1
If we're doing
1
left minus
1
right, then it's 1, and for 3 it's 0. So so right now everything is in the range, so we are good. Okay, but now let's say I add one more element, and maybe yeah, maybe I do 6 first and then I do 8. Let's see for now. So um yeah, so what will happen is, when I do 6, the height of this becomes 0. Okay, I should update everything maybe. Okay, I'll just quickly do this. Okay, so when I add 3, the height of 4, yeah, that of 4 remains 1. But if I look at 2 now, if I keep on tracing back the parents, then the height of this has now become 0 minus 1, which is -1. So we are just doing this minus this. Okay, so now it becomes -1, and that is still okay because we are still in the range. Then if you do an addition of 6, then this is 0, go to its parent. Now both of them are balanced because both are 0 0, so the parent is also balanced, so update this to 0. So update this to 0 and look at its parent now. So we are always going back to the parent and update the height changes if any. So this is 0, this is okay, it's not exactly that, but okay, maybe we need to do some extra bookkeeping to yeah, to make sure of this 1 minus 1 factors. So here you have 1, here you have 2, so maybe like keep whenever you are iterating back, keep a like a, what do you say, like a flag. So flag tells you whether the height increased at all or not. If it increased, then only we're going to have to make these changes. So this becomes, so this remains -1 because yeah, because when I added 6, I did not change the height of 4. The height of 4 is still 1, it was 1 even before 6 was added, so nothing changed for 4. The height of 4 did not increase, so you don't need to trace back any of the parents, the height of the parents will remain the same. So there is some, yeah, this is some what do you say, like case sort of thing you need to do to make sure when you have to go back to the parents to update and when not. So this is just one flag which tells you if it increases the height, then you have to trace back and change. If it doesn't, then we don't need to change. Okay, so yeah, so we keep on doing this, and eventually, let's say when I add 8, then we are going to update the values. So 8 is balanced, 6, this increases the height of the tree. Note that in this case the flag becomes 1. Go back to the parent, and left tree height is 0, right tree is okay, and there was an increase, so we are going to increase this by 1, and go back to the parent. There was an increase on the right side, so change this to 1, and go back to the parent, and there was an increase on the right side, so sorry, this is -1 there was an increase on the right side, so this becomes -2. So at this point, um, yeah, so at this point we know that there is an imbalance. So basically what we're saying is that if the tree is very huge and I want to detect that there has been an increase in the I mean an imbalance, then these values are going to help us to detect. um, and I think you can also possibly implement it using heights. And yeah, I think it should be, yeah, I think same kind of idea should work for heights also. I don't see, yeah, I don't see a catch with it. But yeah, so this is some extra kind of bookkeeping that we need to do. And based on the kind of imbalance, then we're going to appropriately apply this one of these four rotations. So maybe I'll add some more questions on AVL trees. There are few that are already there, but yeah, but I we are out of time, so yeah, so I'll skip this for now. But I'll upload the PDF so you can try this out. If there are any questions, you can reach out to me. And yeah, next for the week 7, we'll meet on yeah, we'll meet on the upcoming Friday, which is 7th March, 6 p.m. to 8 p.m. So yeah, I think that's it for today. So thank you for attending. I'll stop the recording. Okay.